presentation. Our project was on representation learning for motion sequence. Our team leader was Sai. The team members was Roshni, Alexandru, and Venkatesh. This project is recording the first step in a smart workout assistance system. The system takes video feed from users exercising, then provides visual feedback by comparing a user's current pose to a professional trainer's pose, which is stored in the system. This project is sponsored by Dr. Yang and Dr. Lin Li for our IT Capstone 7993 class, Spring 2021. It was advised by Professor Dr. Meng, who is also the instructor of the course. The COVID-19 pandemic has brought to the forefront the importance of promoting a healthy lifestyle. Unfortunately, chronic medical conditions such as obesity, diabetes, heart disease, COPD, and kidney diseases are known for raising the risk of severe illness and death when infected with COVID-19. We want to take a look at preventative measures such as identifying and promoting ways for individuals to improve their health. This would be especially beneficial to those who live in areas hit hardest by the pandemic. Teaching lifestyle choices such as increasing physical activities would then have a profound impact for higher risk individuals. We have developed a novel smart virtual exercise assistant that addresses the health and wellness issues in the United States. The system aims to assist people in physical or rehabilitation exercises by learning and providing visual feedback to the users either during or after training sessions. For the purpose, we generated the visual feedback by overlaying the current user pose with a correct pose. For example, a pose that is collected from a professional trainer or physiatrist. By doing this, the user can directly observe which parts of their pose are incorrect and then proceed to fix them. For a given video feed from a user, our system works in 3 main steps. The first step is to capture and extract the user's pose. This means for each frame in the video feed, we determine the user's main body parts, such as head, shoulders, arms, hips, and legs. The result is a skeleton figure that fits the user's pose in the frame. The second step is querying the correct pose. For each user pose extracted from the video feed, we are querying the most similar pose from the database of correct poses. Here, the similarity between the two poses is considering information like the exercise the poses are belonging to, the time and location of the pose in the exercise, and the degree of geometric alignment between these two poses. The final step is aligning the user's pose and the queried pose. There are different body factors to consider when making this comparison, such as physiological differences between the user and trainer physiatrist. For example, are they taller or wider? Camera views, user pose location, scales, and perspectives. Such differences in camera views must be addressed in order to be able to provide the best feedback to the user. We utilize several deep learning models to learn about these sequence embedding, such as deep autoencoders, transformers, and Siamese 3D convolutional neural networks. Overall, here is the system and how it operates. As you can see, we take the user video feed and we map the points. And then we build the skeleton. And then we overlay the trainer skeleton over the user's pose to identify incorrect training. Project deliverables. These were accomplished through our project milestones. In the first milestone, we installed Python, Jupyter Notebook, and all the required packages. We successfully installed 2 models, LSTM autoencoder and fully connected and convolutional autoencoder. In the second milestone, we ran the existing data provided by our project owners on 4 models. Lastly, in milestone 3, we collected our own data, which consisted of 373 workout videos. We then converted them to pose sequences and created a new data file. We ran the new data file on 5 additional advanced models and compared their performance. The following slide shows all the packages that were imported. As you can see, we made heavy use of TensorFlow. Now we're going to talk about the first 4 models that we used. The first one is the fully connecting convolutional autoencoder model. Here's the code. Next one is the long short-term memory autoencoder. Then the gated recurrent unit, or GRU autoencoder. And lastly, the simple recurrent neural networks, or RNN autoencoder. As you can see, the loss achieved by our 4 models was also tested against 3 different architectures to get a better idea of the overall loss. In terms of the model parameters, we used the mean absolute error, or MAE, loss rate, and Adam optimizer with a number of epochs, or iteration, as 1,000 for the first 4 models. Mean absolute error is a loss function used for regression models. To calculate it, we take the difference between the model's predictions and the ground truth. Then we apply the absolute value to that difference, then average it out across the whole dataset. Adam is a replacement optimization algorithm for SGD to train deep learning models. It combines the best properties of ADA-GRAD and RMS-PROP algorithms to provide an optimization algorithm that can handle sparse gradients on noisy problems. It is relatively easy to configure, where the default configuration parameters do well in most problems. Next, we're going to talk about the 5 advanced models. This is the SQGRU model and the flowchart. This is its corresponding code. This is the SQGRU ATT model's flowchart and its corresponding code. Then we have the SQL Transformer model flowchart, and of course the corresponding code, the SQL Transformer 2 model flowchart, and its corresponding code, and lastly the M Transformer model flowchart and the corresponding code for that model. Along that, we also trained all the advanced models. This is the code for use for training. We also tested the data and loss achieved by the advanced models with 3 different architectures once again. And we also tested our query for accuracy of the code. Query accuracy along with the test data loss and achieve for advanced models is shown below. Now let's talk about the model parameters. On this other hand, we use the mean squared error MSE loss function and an SGT optimizer with a number of epochs or iterations as 100 and shuffle as 15 for these 5 advanced models. Mean squared error is perhaps the simplest and most common loss function. To calculate it, we take the difference between the model's predictions and the ground truth. We then square it and average it across the whole dataset. It will never be negative since we're always squaring the errors. Stochastic gradient descent, or SGD, is merely an optimization technique and does not correspond to any specific family of machine learning models. It is only used to train a model. The advantage of it is efficiency and ease of implementation, which means lots of opportunities for code tuning. Because of these advantages, we use this for advanced models as was needed. We also reduced the iterations from 1,000 to 100 and produced the shuffle idea, since in machine learning we often need to shuffle data. Uniform shuffle guarantees that every item has the same chance to occur at any position. Our project environment required our packages to install and test on both Linux and Windows machines, which were our own computers. A Linux server along with login credential, was provided to us by our project owners and was accessed through Global Protect VPN. We utilized EasyGIF.com to convert our workout and exercise videos to GIF files, which were required for our pose sequences. We also installed VNC on the server, which allowed us to be able to access the machine remotely using VNC Viewer. We had a total of 9 different notebooks or .ipynb files, 2 pickle files which contained our old data and new data, and an object file which was used for testing purposes. In terms of our project experience, we had a great learning experience from our team. We learned a lot about deep learning architectures, how they're being used across different platforms. We also learned about functionalities of each models that were used in this project. Our team was able to accomplish this by working together as a team and sharing knowledge with each other. Not all of us were familiar with Python, artificial intelligence, or any of these particular models. We sorted out the problems by giving solutions at the right time, which was helpful for the project to be completed on time. All of our meetings were done using Microsoft Teams, and we established a weekly meeting cadence, which happened every Thursday at 6:30. During this meeting, we discussed our progress and the tasks that were pending at the time. This was extremely helpful to make sure that we're always on time with our milestones and never miss any deadlines. It also allowed us to correctly sync with our project owners to make sure that we always deliver on what we were promised in the milestone before. Microsoft Teams was our main medium for communication, and everybody was active and quick with their responses. As a secondary medium, we used KSU email, where we communicated between the team leaders and the project owners. Each of our tasks were assigned to each team member by our team leader. Our team leader oversaw each member's progress and also guided them with proper instructions. Our team leader, which was Sai, was organizing the meetings between the team and our project owners, monitoring the progress of the project, analyzing, exploring models, preparing documentation, and also submitting the deliverables on time. The other team members, Alexandru, Roshni, and Venkatesh, were able to analyze, explore models surrounding post-sequence retrieval, and prepare documentation including presentation material. All of us ran a bunch of different models on our machines that were assigned by Sai. For example, in the 5 advanced models, they were divided one each except for the first 2, which was Sai was able to run on the server because it was much faster. Because of the time that took for each one of these models to run, Sai successfully coordinated with each one of us to make sure that we run it ahead of time to be able to have it done by our milestone. Apart from specific responsibilities, all team members contributed equally by installing the packages, running models, and also producing ideas to enhance the project. Some of our project challenges were, in the beginning, was sharing one virtual machine among 4 students. We quickly realized that this virtual machine only allowed one user instance, which means we could not all use it at the same time. This became an issue, so we had to utilize our own machines. In the later part of our milestone, our team leader used a virtual machine while the rest of the team used their own machines. This did mean different performances, so we had to run them against our own machines, which took a little bit of time. For example, we had to get these models started about 4 to 5 days before the milestone was due to make sure that we could accomplish it on time. Another challenge we faced sometimes was the inability to log into our virtual machines. This was mostly caused by VPN issues. our project owners were able to assist and provide fixes for us. We wanted to thank our project owners for allowing us to accomplish this project and guiding us all the way through, along with our professor, Dr. Han. Thank you for listening to our presentation, and let us know if you have any questions.